For over 3 decades, 34 years to be exact, the Hubble Space Telescope has peered deep into the cosmos, revealing galaxies far away, the formation of stars, the demise of suns, and the intricate structure of the universe. It was crafted to serve as our portal to the distant past, gazing into the vast depths of space and time. Yet recently, it did something no one foresaw, something it was never intended to do. It witnessed a phenomenon that, by all standard assumptions, should have remained invisible. And from that moment, everything shifted. Hubble detected something that challenged its very purpose. A burst of energy so brief, so intense, and so evasive it pushed the limits of what we believed light and distance could convey. In a remote, incomprehensible corner of the universe, an area the telescope had surveyed many times before, a sudden, potent flash of ultraviolet light erupted. It didn't come from a known source like a supernova or a quasar. It was something new, something unlike anything Hubble had observed in its long lifetime. This instrument, originally engineered to monitor slow, gradual cosmic processes, had stumbled upon a fleeting and puzzling cosmic signal. What made this encounter so remarkable wasn't only the event itself, but that Hubble managed to capture it at all despite its aging instruments and limited sensitivity. The light originated from a galaxy so remote that its photons had been traveling for billions of years before finally striking Hubble's detectors. But the signal didn't align with any previously recorded phenomena. It flickered briefly, surged in brightness, and vanished in a blink, almost like the universe itself had momentarily blinked. Initial reviews dismissed the anomaly as a hardware glitch, possibly a cosmic ray striking one of Hubble's sensors. But the data didn't support that. The signal had a clear structure, a pattern that couldn't be explained by noise. The ultraviolet intensity was higher than anything known from stellar activity, and notably, it came from a region of a galaxy previously observed as dormant, inactive, and devoid of new star formation. Hypotheses began to emerge. Some astronomers speculated Hubble had captured the birth of a magnetized, supermagnetized neutron star formed after a supernova. Others suggested something even rarer, a fast blue optical transient, or FBOT, a new class of powerful explosions that appear and disappear within days, unlike traditional supernovae that unfold over weeks. But even these theories fell short. No FBOT had ever been observed so early in its development or with such ultraviolet strength. Whatever this was, it was faster, brighter, and more sudden than anything seen before. What made the event significant wasn't just its uniqueness, but what it implied. If Hubble, an aging observatory, could detect something so fleeting and hard to observe, it meant the cosmos might be filled with similar hidden events, constantly occurring just beyond our observational limits. It suggested the night sky was far more dynamic than previously believed. The vast spaces between stars might not be quiet and still, but instead alive with fast, brilliant flashes appearing and vanishing too quickly for us to catch. And yet, Hubble saw it. Despite its age, outdated hardware, and infrequent maintenance, the telescope caught a glimpse of something nearly beyond its reach. It wasn't just a testament to its construction, but to the enduring power of curiosity-driven exploration. This unexpected detection pushed astronomers to reconsider the possibilities buried within Hubble's archive. If such a brief flare could be recorded during routine imaging, how many others lie hidden in decades of stored observations? Hubble's purpose, once limited to documenting ancient, slowly evolving phenomena, now included the potential to track sudden and elusive cosmic outbursts. This discovery reshaped how scientists examined Hubble's data. They began using machine learning algorithms to search old images not for the usual spiral arms or faint galaxies, but for irregularities, flickers, and sudden light events previously discarded as static or interference. A new approach emerged, observing the vast universe. This wasn't about long, patient exposures anymore, but about catching the abrupt, high-energy eruptions of cosmic activity. Beyond astronomy, the implications resonated more deeply. Philosophers and cosmologists began to wonder what this meant for our understanding of reality. If space is scattered with brief, powerful light bursts undetectable by the naked eye or traditional telescopes, then the universe may be more volatile and vibrant than previously imagined. These flares could be signatures of exotic matter or traces of physical processes beyond anything our labs on Earth can reproduce. Some even speculated the flash was a white hole, the theoretical reverse of a black hole, expelling matter and energy in a sudden, short-lived burst before collapsing. Others proposed the flare was a bridge event, something predicted by certain models of string theory or multiverse frameworks, where higher-dimensional interactions spill energy into our universe. While these remain unconfirmed, the fact that they were seriously considered shows how deeply this single detection disturbed the established order of cosmology. And yet, what made it all the more astounding was that Hubble wasn't supposed to see anything like this. It was built for patience, for capturing the graceful structure of galaxies, the subtle glow of nebulae, the long fade of stars in their final stages. It wasn't made to detect second-long flashes or sudden distortions in the fabric of spacetime. Like a lighthouse scanning the sea, it was meant to observe with steadiness, not chase after flashes in the dark, but it did. Like a tired sentinel glimpsing something unexpected out of the corner of its eye, Hubble caught a brief apparition at the edge of perception. What happens next is critical. If even a fraction of the universe's energy phenomena occur this rapidly and brightly, then our understanding of cosmic evolution is incomplete. It hints at an entire class of astrophysical events we've missed, not because they're rare, but because they vanish before our tools can register them. It suggests we need a new generation of telescopes, not necessarily more powerful, but faster, devices capable of watching the sky in real time, not through static, prolonged exposures, but through rapid snapshots that capture the tiniest flickers. This also could reshape how we search for extraterrestrial life. Until now, we've looked for repeated signals, enduring emissions, or steady patterns. But what if intelligent civilizations or unfamiliar technology send signals as bursts? What if they use high-energy flashes to avoid detection or conserve power? It's possible we've already missed such transmissions, mistaking them for random noise. Hubble's unexpected detection may be the first clue that they're out there and that we need to change not just our instruments, but our assumptions. From a technological perspective, this discovery also serves as a quiet challenge to the belief that older instruments are no longer useful. Hubble was designed in the late 1980s, built with the science and technology of a pre-digital world. While it's been upgraded over the years, it's still a legacy tool by modern standards. And yet, it achieved what no newer device had. It discovered something genuinely new. That alone is a powerful reminder that older tools can remain relevant. When paired with open minds and rigorous analysis, the event will be examined for years to come, not just the light itself, but the path it opened. Researchers are already developing models to explain what kind of event could produce such intense ultraviolet energy in such a short time. Others are cross-checking the location with earlier infrared and radio observations, searching for any prior signs of activity. But for now, the origin remains a mystery, another question among many hanging in the sky, and that's part of the magic. After more than 30 years, after thousands of orbits and countless images, Hubble is still surprising us. It's still challenging the assumptions that shaped its design, still telling us stories the cosmos hasn't yet finished speaking. This latest observation may be its most exciting yet, not just because of what was seen, but because it signals that the universe is still bursting with untold secrets, waiting to be revealed by eyes we've yet to open. The flash Hubble caught isn't just a brief anomaly. It's a signpost, a reminder that the story of the cosmos isn't only written in slow, stately arcs, but also in sudden, brilliant sparks. That some of the universe's mysteries aren't hidden in the ancient glow of time, but in the instant shimmer of the present. And perhaps most astonishing of all, Hubble, nearing the end of its service life, was the one to catch it, not through design or intention, but because it was still watching. This moment has energized space agencies around the world. If such rapid, luminous events exist and can be detected by a decades-old telescope, what could a purpose-built, fast response ultraviolet observatory find. Planning is already underway for the next generation of instruments focused not just on deep vision, but on speed. The calm sky we thought we knew may actually flicker like a pulse, subtle, rapid, fleeting. And if Hubble saw it once, maybe it has seen it more than once, quietly recorded in its vast archive, waiting to be found. More than anything, this moment reignited a sense of wonder. It reminded a new generation of scientists why they look to the stars not only to understand, but to be amazed. Awe doesn't always arrive in the form of vast structures. It can appear in a flash, a fleeting glimpse of something unknown.